Today is April 16, and I want to do a calc lecture here for you. So a couple administrative things. I do want to alert you, as I had to remind myself this morning, we have 4 more lectures left in this class, which I don't think I fully appreciated again until this morning. I didn't realize that. But we have 4 more lectures. 1 today, 1 tomorrow, 1 Tuesday of next week, and 1 last one on Wednesday. Wednesday is the last day of instruction for the semester, is my understanding. And then I believe we have a final exam on the 25th, Saturday the 25th of April. So we have several major topics still that we need to get through. So today I'm planning on talking about something called the ratio test. And usually I would follow up the ratio test with another result called the root test. But I'm basically not going to do that. I'm going to basically excise the root test from the course. If you're interested in learning about the root test, it's a standard part of most Calc 2 courses. But in my opinion, we can get by without it. And today also I want to talk about power series, which are a sort of the fundamental notion of this new way of thinking about functions that I've been sort of advertising to you throughout the semester. Okay, so that's what we're going to do today. Hopefully we will conclude our discussion of power series in general tomorrow, so that we can hop into Taylor series on Tuesday and Wednesday. All right, so that's sort of how I'm envisioning this class going from here on out. I do want to say something about the slip that I assigned yesterday. I just want to talk about it a little bit. Here is the problem statement. If you recall, many of you turned in your post-lecture slips and answered this question, or these questions, rather. So please take a look here. The question was, taking this sequence here, this series, rather. I'm sorry, my brain is not quite online yet. This series, which is like an alternating p-series, right? You can see the terms are 1 minus 1/4 plus 1/9 minus 1/16 plus 1/25, etc. That's an alternating p-series with p equal to 2. Okay. The question is whether or not it's absolutely convergent, conditionally convergent, divergent, or what, you know. So I just want to tell you what the answer is. The answer is that it is absolutely convergent. Now, if it is absolutely convergent, it cannot be conditionally convergent, right? Because if you look back at the definition of absolute and conditional convergence, which we saw here yesterday in our lecture. So what does it mean for a series to be absolutely convergent? It means that this associated series, where you apply the absolute value bars to the sequence of terms, is a convergent series. Okay? And then we have something called the absolute convergence test, which says that if a series is absolutely convergent, then it must necessarily be convergent. Okay? So you cannot have an absolutely convergent series which is divergent. Such a thing is an impossibility as per the absolute convergence test. Okay? But you can have a convergent series which is not absolutely convergent. Okay? And those are called conditionally convergent series. A series is conditionally convergent if it satisfies 2 conditions. If it is convergent, if it is convergent, but that when you apply the absolute value bars to the sequence of terms, you get a divergent series. And the most famous example of a conditionally convergent series, of course, is the alternating harmonic series. Now, in looking at this series here, I claim that this series here is absolutely convergent. And the reason is because if you apply the absolute value bars to the sequence of terms here, okay, what do you obtain? Or what is the effect? The effect is to transform this alternating sign gadget, -1 to the n plus 1 power, is to transform that into just simply a 1. Okay? So that instead of looking at the sum of -1 blah 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 over n squared, we are instead are looking at 1 over n squared, the sum from n equals 1 to infinity of 1 over n squared. And that is well known to be a convergent series because it's on the nose p series with p equal to 2. And 2 is greater than 1, so it converges. Hence, what we're saying is this thing is absolutely convergent because it satisfies this definition of absolute convergence. And as a bonus fact that we get to deduce from this, we can use the absolute convergence test to declare, that must mean that this series here is convergent. This series converges. Okay? And like we talked about yesterday, you could use a computer to estimate the value of what that convergent series is equal to. I believe the answer is pi over 12, but I've not confirmed that or anything. That's just, I'm digging up some relic that's very deeply embedded in my head that I learned a very long time ago. So take that with a grain of salt, but I think it's, or I'm sorry, pi squared over 12. Pi squared over 12, I think, is the right answer. Which is crazy, but we don't have time to really elaborate on that, so maybe I'll not talk about that. Yeah, so the answer to this one, is it conditionally convergent? No, it can't be. It's absolutely convergent. And absolute convergence and conditional convergence are mutually exclusive. You cannot be both at the same time. So if you know something is absolutely convergent, it can't possibly be conditionally convergent. Just look at the definitions if you don't believe me. You really should if you're skeptical or if you're unsure or you're unclear on that, right? These are two mutually exclusive situations. You cannot have both happening at the same time. So because we can see that this thing is absolutely convergent, this is true. This statement here is false. It's absolutely convergent and hence it is convergent. Okay. So, like I said, today I want to talk about the ratio test and hopefully get into start talking about power series. So the ratio test. So today, just to be clear about the date, for posterity's sake, today is April 16th. Okay. Oh, I realize that now that I've done this, where I put the date on there, I can't reuse these things like next semester or something like that. Oh well, I don't know. I mean, okay, why am I wasting time? I'm not sure. So let me just give you the idea behind the ratio test. So I want you to recall geometric series for a second. Recall the subject of geometric series for a sec. So what were geometric series? These were series of the form sum from n equals 0 to infinity of a times r to the nth power. So the terms look like a plus ar plus ar squared plus ar cubed, etc. And we can keep going. And what I can do is write the nth term of this sequence. That is this to say this. I mean, you can think of it, the nth term as being sort of a general formula for the sequence of terms here, but maybe I'll write it like this: a times r to the nth power. And then the next term after that is a times r to the n plus 1 power. Okay, so that's a geometric series. Now, one thing I want you to notice about when a geometric series converges, okay, suppose that this is a convergent geometric series, and we know precisely the conditions under which that happens. That happens when the absolute value of r is less than 1. You can go back and review our lecture on geometric series to see that if you don't recall that, but that's a fact. This thing will be convergent if the absolute value of r is less than 1. So think about what that means for the sequence of terms for just a moment. What it means is that the ratio of any two subsequent terms, that is to say any two terms which are next to each other, if you take the right term and you divide it by the left term, the number that you get is in a geometric series is always the same. It's always equal to r. And if r is less than 1 in absolute value, that implies the convergence of this series. That, in other words, what I'm saying is that the fact that the terms decrease in some sense by a factor of r, where r is less than 1, so it really is a decrease. So imagine like r is 1/2, right? If r is 1/2, then this term here is half the size of that term. This term here is half the size of that term. And not wishy-washy, it's exactly equal to a half of the previous term, right? And that kind of decrease is powerful enough to cause this set of infinitely many numbers to add up to something finite. Okay? This is the idea behind geometric series. Maybe I'll say it one more time because it's the way I think about it, honestly. But maybe this hasn't been sufficiently transmitted to you yet. So I'm going to say it one more time. So let's open up our minds for a second and open up our ears. Please listen to what I'm saying. If you think about how the sequence of terms here is decreasing in a convergent geometric series, that it must necessarily be the case that these terms are decreasing, right? I mean, let's forget about alternating geometric series, whatever. Let's just think about when the geometric series is, the sequence of terms is decreasing. Then what's going on here is that the ratio, to get to the next term from a previous term, what you do is you multiply by a number which is less than 1. And you just keep doing that over and over and over again to obtain the sequence of terms in this geometric series. And the fact that this geometric series converges if r is less than 1 means that that ploy, that stratagem of multiplying by this number that's less than 1 over and over and over again to generate the sequence of terms, that is making the sequence of terms go to 0 fast enough that this series is convergent. Okay? Now, what's special about a geometric series is that that ratio is the same between any two subsequent terms in the series, in the sequence of terms of the series. So what if instead we had a result which slightly generalized that idea to a sort of, instead of thinking about or worrying about what's going on with the ratio precisely, we have some sort of maybe fuzzier way of approaching that notion of a ratio of subsequent terms which is less than 1. And that's what the ratio test does. So let me state now the ratio test. So if I wanted to write down the insight that I just sort of gave you, maybe I'd say it like this. If this series is convergent, this sort of says that this process, I'm being kind of vague here, I'm not wording this well, that this process of multiplying by r causes the sequence of terms to go to 0 fast enough to induce, or I'll say produce, a convergent series. There's a lot of sort of waffly words here, but this is the idea. Okay, so maybe let me try to situate this idea in the context of something like the divergence test. So recall the divergence test says that if you have a convergent series, then it must be the case that the sequence of terms goes to 0. But we know that just simply going to 0 is not enough to guarantee convergence, right? The converse is false. And the counterexample that you should have in your brain is the harmonic series. The harmonic series has a sequence of terms which is going to 0, but unfortunately, well, I don't know, unfortunately, this is just the state of affairs. I'm not trying to put any value judgment on it. It diverges. In other words, the sum of those numbers blows up and goes to infinity. Okay? So, right. Wow, I'm lingering way too long on this. So a key issue then is the speed with which the sequence of terms goes to 0. The speed with which a sequence of terms goes to 0. And what I'm saying is that this scheme in geometric series, where we multiply a number, a fixed number a, repeatedly by a number r which is less than 1 in absolute value, that scheme causes the sequence of terms to go to 0 fast enough. Okay, that's what I'm saying. That's all I'm saying. Fast enough for what? Fast enough to produce a convergent series. Other convergent series have the same property. Think about the sum of 1 over n squared. That's a p series, p equal to 2. It's convergent. It goes to 0. Its sequence of terms goes to 0, right? Just like the harmonic series. But the difference is that it goes to 0 fast enough to produce a convergent series. Am I making any sense here at all? I don't know. It makes sense, perfect sense to me. But these are hard ideas. These are not easy ideas, and they're probably very different in nature to anything that you've seen before in your life when it comes to a math class. Because here we're being hard-nosed about our approach to the concept of infinity. Whereas before, maybe it was fuzzier, and it was sort of vague, and it was like a meme or something. But now we're going to take it really seriously. This issue of fast enough is super important when it comes to this idea of infinity and the more general topic of asymptotics, which is, in some ways a dominant force in our life, even though we might not fully be aware of that. Okay, so let me actually state the ratio test with this in mind. So suppose we have a series, sum of a sub n, okay, with has a sequence of terms which is non-negative, or that is rather positive. Suppose we have a series with a sub n always being 0, or I mean whatever. Okay. Suppose further that we have the limit as n approaches infinity of a sub n plus 1 over a sub n. So this is the ratio of subsequent terms in the sequence of terms. Okay. Suppose that this is equal to, let's call it a number r. R will stand for ratio. Okay. Then we can say a couple things, several things. If r is less than 1, okay, then the series is convergent. If r is greater than 1, then the series is divergent. And if r is equal to 1, then you can say nothing. If I was good with video, this is where I'd play a Simpsons clip of radioactive man getting consumed by a flood of acid, and he's filming a movie, and the director tells him that for his safety he should wear goggles, and radioactive man, while getting drowned in a flood of acid, says, "My eyes, the goggles do nothing," and he says it with a funny accent. You should look that clip up. But in the ratio test, okay, if r is equal to 1, you should say to yourself, my eyes, the goggles, they do nothing. The ratio test does nothing in the case where r is equal to 1. You get no insight. And I won't say that you get drowned in a bath of acid or anything like that, but anyway. Okay, so ratio test is pretty sweet, right? It sort of is a generalization of this idea that subsequent multiplication by a number r which is less than 1 is sufficient to guarantee a convergent series. And if you look at this condition here, that's sort of saying the same thing, but in a slightly more general way. This thing here, this condition, that the limit is a sub n plus 1 over a sub n being equal to r, if that r there is less than 1, then it sort of feels like, to get subsequent terms in the sequence of terms, what we do is we multiply by this number r. Now, not exactly, right? If I look at, because this is a statement about the limit as n approaches infinity of that ratio. But it's good enough. It's good enough that this is the truth right here, right? The ratio test is the truth. Hopefully you understood that 20-minute little diatribe there on this idea. But I like the link between these two ideas. Let's do an example. Do you remember doing a slip a while back where I asked you about this series, the sum from n equals 1 to infinity, what was it, n over e to the n? Or did I put n squared there? I can't remember. N over e to the n. So here was a series. Do you remember it? It was yeah, this series here. We had to use the integral test, and you had to do integration by parts, and it was gross, and you didn't like it, and because who likes doing an integral, right? So certainly, if there was some other way of doing this problem, like the ratio test, we should probably exploit that. So let's do that. Let's call this sequence of terms here a sub n. Okay, what we want to examine if we're going to invoke the ratio test is the limit as n approaches infinity of a sub n plus 1 over a sub n. This is what we want to think about, right? Look, there it is, okay? Oh, somebody asked. It must be geometric to use the ratio test. No! No! What's great about the ratio test is that it generalizes the sort of idea of convergence that is established by the example of geometric series. All right, geometric series gives us a way of understanding a family of convergent series. And that family of convergent series is characterized by the fact that the way that you obtain that sequence of terms is by multiplication by a number r, which is less than 1. I'm saying if you look at the statement of the ratio test here, that's sort of saying that because the ratio of the subsequent terms in the limit is equal to r, you can kind of think of it like the sequence of terms has this same sort of property. And so you can definitely use this in contexts which are not geometric. Thank you for the question. Let's return to this example. Let's look at the limit as n approaches infinity, a sub n plus 1 over a sub n. So what is a sub n plus 1? Where should I write? Oh, maybe I'll write this here. This is equal to the limit as n approaches infinity. So n plus a sub n plus 1, what it is what we obtain by replacing the n here and the n there by n plus 1. So what that is n plus 1 over e to the n plus 1 power. Right? That's a sub n plus 1. It's hard to disagree, I hope. And then a sub n is just what we see in front of our faces, right? So this is going to be n over e to the n. And this is a fraction of fractions, right? Are we all comfortable with that? So now we can do some basic, I don't know if you call it algebra or if you call it arithmetic, but we can flip-flop the denominator like this. And then the magical thing that happens here is that notice that the e to the n over the and the e to the n plus 1, they interact, don't they? What is the quotient of e to the n over e to the n plus 1? That's equal to 1 over e, right? You can think of it like the e to the n's cancel. And I can move this n over so it's underneath here. And so we get this quantity. Y'all agree? Now, this is a dumb constant, right? It does not depend on n. It does not change as n clicks through the positive integers, right? As n gets larger and larger. It does not change or anything like that. So we can move it outside the limit if we like. And now the question is, what is the limit as n approaches infinity of n plus 1 over n? Well, hopefully you're well versed enough in all of this stuff and you've done it enough times that you more or less immediately know that that's 1. But if you don't know that yet, that's okay. That's fine. There's a number of ways that you can go. You can use L'Hopital's rule if you want to for an interpolating function for this sequence, or you can do what I often find myself enjoying, which is factoring out the highest order term, which is that n from the numerator, so that these n's cancel. When n goes to infinity, this 1 over n dies. And so in the limit, what we get here, this limit here is equal to 1. So when we multiply that by 1 over e, we get 1 over e. And you know what this is? This is what's playing the role of r over here. Now what can we say about 1 over e? Well, you should know e is like 2.714, I think. I don't know. Something like that. But in particular, it's bigger than 1. E is bigger than 1. So 1 over e is less than 1. Is that clear? And so, by the ratio test, the given series converges. Okay? Now, I don't know about you. I don't know about you. Maybe you really love integrals. Maybe you love integration by parts and all of that. But to me, this argument it gives me way more insight into why this series here converges, personally. Because, so what is this sort of saying? This is sort of saying that when n is very, very, very large, if you look at n over e to the n, okay? If you look at the sequence of terms when n is very, very large, the way you should think about this statement that the limit is equal to 1 over e is that to get, let's say, the millionth and 1th term, what you do is you take the millionth term and you multiply it by 1 over e to get the millionth and 1th term. Do you see what I'm saying? That when n is extremely large, the ratio of subsequent terms is 1 over e, and that's less than 1. So it's kind of like this series here is kind of, not exactly, but almost, and good and well enough behaving like a convergent geometric series. That's sort of the idea, okay, behind the ratio test. It's a very interesting idea. It's fun to think about. And I mean, like, you know, if you took your computer and you computed n over e to the n, where n is equal to 1,000,000, and then you divide it by n over e to the n, where n is 1,000,001. You do that upside down, right? Then you'll get 1 over e. Yeah. Okay. Here is a pro tip, a tip from the pros, a pro tip. Here's a life hack for you. A life hack. Life hack. Here's a pro tip. Pro tip. Ratio test is great. Well, okay, so it is great, but it's particularly great for series involving exponentials and, in particular, one thing that's going to be of great interest to us are factorials. Okay, so let's just really fast recall factorials. So recall factorials. This is written like this: n bang, or n factorial. Computer scientists sometimes, I've heard computer scientists say n bang, whereas math folk typically say n factorial. N factorial, what is it? Is the product of the first n positive integers. And we say by definition 0 factorial is equal to 1. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, 6 factorial is 720, 7 factorial is, now this I think is hard. Is it 5040? So how am I doing that? The way that I'm doing that is I'm taking the previous number, okay, and I'm looking at, so if I want to know 4 factorial, I can take 3 factorial, which is 6, which is 3 times 2 times 1, and multiply that by 4, right? So 6 times 4 is 24. So that's how I'm getting this number. And 24 times 5 is 120. But like, for example, what 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And another way of writing that, of course, is 7 times 6 factorial. Okay? Factorials are extremely important for us. You will see why. But just take my word for it. Why would I lie to you about that? Okay? So the pro tip that I'm giving you is that ratio test is fantastic when you have a series which involves exponentials and factorials. So let's look at the following example. Yeah. The sum from n equals, let's say, 0 to infinity of, let's make it an alternating series. So let's put a -1 to the n there, and let's have the numerator, let's put a 3 to the n, and let's put n factorial down here, okay? And, oh, god damn it, okay, let's think about this crazy series here. Now, one thing that I'd like you to notice about this series is that it is an alternating series, right? 3 to the n over n factorial, when n is 0, 1, 2, 3, etc., that's a positive quantity. So if I tag this thing with a alternating sign gadget, then certainly we're going to have the signs of these terms alternating between negative and positive. Hopefully you can agree with that. Now notice, if I want to use the ratio test, note one of the important assumptions of the ratio test. You see it? One of the important assumptions is that a sub n is greater than 0. That is to say, it's important that the sequence of terms be positive in the ratio test. Here we don't have that. So it seems as though this that the ratio test cannot possibly apply to this series because we have negative terms. Okay? It really is important that in the ratio test that the sequence of terms be positive. So are we just, out of luck here? Do we have to use some other method? No. So here's what we're going to do. Instead of testing, this is important, so please listen, because we're going to be doing this a lot. Instead of testing this series for convergence, and even, so I might even give you the instruction, test for convergence. So instead of solving that problem, instead what we're going to solve is we're going to find a stronger property, or investigate a stronger property of series. And that stronger property is a property stronger than convergence. That stronger property is absolute convergence. So instead of investigating this series, we are instead going to test this thing and its convergence. We're instead going to test this thing and investigate this thing for absolute convergence. And why is that? Well, so first point, if we know this thing converges, then by the absolute convergence test that we talked about yesterday, if a series is absolutely convergent, then it is convergent. So if we can determine, if we can figure out that this thing is absolutely convergent, then we win. We win this problem. We defeat this problem, right? Because then we know it converges. Agreed? Okay, so that's what we're going to do. We're going to try to investigate this thing. But the second point is that if we investigate this thing for absolute convergence, then we're dealing with a series whose sequence of terms is positive, strictly positive. Because we'll be taking the absolute value of this crazy guy here. Yes? Okay, so we're going to, in fact, let's test for absolute convergence. This is, strictly speaking, a harder condition to meet because we know there are convergent sequences which are not absolutely convergent. They're called conditionally convergent series. Okay? So this is stronger than convergence. But this, passing to this question of absolute convergence allows us to use the ratio test. So let's do that. So instead of looking at this series, we're going to look at the absolute value. Okay? Now, one thing you should know about absolute value is that it behaves really well with respect to multiplication and division. So another way of thinking about this is that this is equal to the sum from n equals 0 to infinity of the absolute value of -1 to the n times the absolute value of 3 to the n over the absolute value of n factorial. Okay? That you can sort of move the absolute value bars as long as you're dealing with multiplication and division. This is totally legit. Okay, I've got 14 minutes. Never mind. Yeah, so what is the effect of these absolute value bars on these various quantities? Well, can we agree that 3 to the n here, 3 to the n here is always greater than or equal to 0 for n equals 0, blah, blah, blah. Well, it's always greater than or equal to 0. So the absolute value of 3 to the n is just 3 to the n. Similarly, n factorial, you can look at this sequence of numbers over here. N factorial is always greater than or equal to 0. It's always greater than 0. So the absolute value of n factorial is n factorial. What is the absolute value of -1 to the n, though? Well, -1 to the n is always either -1 or 1. And the absolute value of either of those quantities is 1. Agreed? So we can rewrite this whole thing here, okay, as the sum from n equals 0 to infinity of 3 to the n over n factorial. Okay? So, in fact, testing this series for absolute convergence is the same as testing this series for convergence. Can I say it again? Testing this series for absolute convergence is the same as testing that series for convergence. Okay? This series is amenable to the ratio test because its sequence of terms is positive. So let's use the ratio test. And if we do that, we're going to look at the limit as n approaches infinity of a sub n plus 1 over a sub n, where now this is playing the role of a sub n. Okay. So what's a sub n plus 1? Well, that's what we get by replacing n by n plus 1. So this is 3 to the n plus 1 power over n plus 1 factorial. Don't be weird. It's the entire n plus 1 that's getting factorialed. Okay? Then we're going to multiply this by a sub n. What's a sub n? Well, it's the reciprocal of, sorry, what's 1 over a sub n? It's the reciprocal of this thing here. So that's, I think the words I'm saying is correct. This, it's that. Okay, hopefully everybody can understand that. Now this is an important moment. So 3 to the n plus 1 over 3 to the n, what is that equal to? Well, that's just 3, right? This is one factor of 3 greater than this one, right? So this is these two guys, they cancel and become just a 3 upstairs. And how does n factorial over n plus 1 factorial work? So let's do a little side calculation. N factorial over n plus 1 factorial. You might pause the video and think about it, but let's just think about, let me do the calculation here. N factorial is the product of the first n positive integers. So that's n times n minus 1 times, now I'm going to just continue the pattern, times 3 times 2 times 1. You agree? And downstairs, n plus 1 factorial. Well, that's just n plus 1 times n minus 1 times times 3 times 2 times 1. So the quotient looks like this. Do you see the massive die-off that happens here? This n and that n destroy each other. This n minus 1 and that n minus 1 destroy each other. All of these numbers destroy each other. Everything dies. Everything dies except for this n plus 1 right here in the denominator. In other words, what I'm saying is that this is equal to 1 over n plus 1. Okay? So over here, when we're looking at n factorial over n plus 1 factorial, what we're left with is 1 over n plus 1. That is to say, an n plus 1 downstairs. That is very tricky for students, in my experience. Okay? All right. So, cool. Cool. So now as n goes to infinity, what happens to this? I think it's pretty obvious, isn't it? The upstairs is just 3 forever, whereas the downstairs is blowing up to infinity. So this quotient must be going to 0. And the key thing about 0, you know that 0 is less than 1, right? 0 is less than 1, it's true. So by the ratio test, the sum from n equals 0 to infinity of negative 1 to the n over 3 to the n factorial is absolutely convergent. And so by the absolute convergence test, the series is convergent. Somebody asks, why is the second term in n plus 1 factorial n times n minus 1? So down here, so what n plus 1 factorial is the product of the first n plus 1 integers. So if I start from the top, or maybe I'll start let's read from right to left. So the first integer, positive integer, is 1, the next is 2, the next is 3, and we go, so we're doing 1 times 2 times 3 times dot dot dot, look at my pen, times n minus 1 times n plus 1. That's what n plus 1 factorial is. Does that answer your question? I have no idea. I wouldn't say that the second term of n plus 1 factorial is n times n minus 1. I like to reserve that word term for summands. And there's no summands really happening here. There's just n plus 1, it's just n plus 1 times n minus 1 times dot 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 times 3 times 2 times 1. That's what n plus 1 factorial is. Okay, so cool, that's that. All right. How the hell are we going to do this semester? How is this going to happen? No more dithering, huh? That's the ratio test. So here's your post-lecture slip. Here is your post-lecture slip. Well, let's go. Test the following for convergence. And what should I make you do? It's a good question. What should I make you do? Okay. Let's try this. Let's do the sum from n equals, I don't care, it doesn't matter, 2 to infinity of n squared over, now this is tricky, 2n plus 1 factorial. Determine whether this is convergent or divergent, okay? That's your post-lecture slip for today. So this is, what is it, April 16th? All right, so I want you to solve that problem and submit it to me by the end of today. Now, I've got 5 minutes, so you're not allowed to just leave. Sorry there. You're not allowed to just leave. Because I've got 5 minutes. I have 5 minutes of your time and your life in my hands that I can do whatever I want with. Got it? And so the way that we're going to spend that 5 minutes is to talk about power series. I'm even going to get a new sheet of paper. So we've been talking about series a lot. Series quite a bit. And today we are going to introduce a way of representing functions as infinite series. We're going to bring together the notion that we've been talking about for the last week or 2 weeks or so, and we're going to combine it with the fundamental objects of study in single variable calculus, which are real valued functions of a single real variable. Okay, so power series. These are a power series is a series of the following form. Sum from n equals 0 to infinity of a sub n times x to the nth power. So the idea here, maybe I'll write out the sequence of terms. This is the same thing then as a sub 0, and x to the 0 we're just going to take to be 1 always, plus a1 times x, plus a2 times x squared, plus a3 times x cubed. Maybe the way you can think of, and where these are, so a's, the a's here are just numbers. They're just constants, okay? And the way you should think about this crazy object, maybe, the thought bubble that you should have, but you should never say out loud in front of a respectable company, is that this is like an infinitely long polynomial. Something like that, right? It's like, it looks like a polynomial, and if you were to cut it off at some point, then you really would just have a polynomial. For example, if I was to cut it off here and not write any terms after here, I would have a degree 3 polynomial that I was looking at. But what these dot dot dots here suggest is that this pattern goes on forever and ever and ever. Okay? And so it's an infinite series for real. A power series is something that looks like that. And the idea here is that we will use power series as a new way to represent functions. A new way to represent functions. Okay? Power series are going to represent, give us a new way of representing these the objects of study in single variable calculus. Okay? For example, now this is very sophisticated, and I don't expect you to understand this yet, but I just want to show you what I mean when I say it's a new way of representing functions. It turns out that, for example, it turns out that e to the x, like our best friend, e to the x, okay? There is a completely new way of representing this function e to the x using this technology of power series. It turns out that e to the x is equal to the sum from n equals 0 to infinity of 1 over n factorial times x to the nth power. This is one of the reasons why factorial is so incredibly important, is because it arises in this power series representation of the function, the familiar function e to the x. Okay? So what's playing, if in comparing this with that, what's playing the role of what? Well, I guess a sub n here is 1 over n factorial. Where am I in terms of time? Oh, I've got 30 seconds. Okay. Oh gosh, I'm a little scared. Do I want to do this out loud? Sine of x? Oh gosh, am I doing this off the top of my head? I believe that the power series representation of sine of x is like this. It's -1. I'm not trying to scare you, so just relax. To the nth power over 2n plus 1 factorial times x to the 2n plus 1 power. Okay, a new perspective on this incredibly important function, sine of x, as an infinite series. What am I saying? I'm saying that if you want to calculate the sine of 1.7, what you can do is plug in 1.7 into this infinite series, and that infinite series will converge to the value of sine of 1.7. If you want to calculate the value of e squared, what you can do is replace that x right there by 2, and that series will be a convergent series, which will converge to the value of e squared. That's what I'm saying. Okay? Now, the amazing thing about this power series stuff, okay? The amazing thing about this power series stuff is that it allows you, one, to do calculus, not with representations of functions like this or like that, but rather like this. Calculus of power series, okay? And two, it allows you to access functions now which we previously would not have been able to do calculus with, or that we didn't have any other good representation for. So you know that when you're thinking about a function in general, right? Like if I draw a random graph of something like that, right? You don't have a clue what the underlying function or formula for the function of that random ass curve in the plane is, right? You have no idea what it is. But you can use geometric information in this picture, okay? You can use geometric information in this picture to write down these coefficients a sub n to give a power series representation for that function. Okay? So that if in principle you know everything that there is to know about this curve, then you have a way of representing that curve as the graph of a function. So what that allows you to do is find functions which are missed by these e to the x's, the sine of x's, the cosine of x's, the tangent, all of the sorts of functions that we find very pleasant and amenable to work with as far as calculus is concerned. Those cannot possibly cover everything. But now what we see is that there's a way of covering those missing gaps, or at least some of those missing gaps, by using an infinite series representation of them. Okay, wait, I'm going off here. Okay, I know you didn't understand what I just said, and that's fine if you really didn't understand what I just said. I don't expect you to know that, but I'm just telling you why you should care. You should care. I mean, frankly, the only reason I think that you should really care, that you should take this on board, is that it's a new way of representing this concept of function. Period. But I'm saying that there are ancillary, additional benefits that come from studying this, from studying the concept of function in this new way, right? That there is not vacuous to have this new representation. It really does produce something new and novel that we've not seen before. All right, I'm over 3 minutes over time. I can see that. Forgive me or not, I don't give a shit. Here is your post-lecture slip for today. I'll just give you a hint about it. Use the ratio test, okay? Use the ratio test. Cool. And that's that. If you have any questions, I'm going to open up a Zoom thing right now. Somebody does ask, prior to the final, will we be given the chance to look at our last quiz, because I felt that it would have been helpful to have for the midterm we took. A quiz? I don't know what you're talking about exactly, but you'll definitely get your midterm scores back with some feedback on the midterm, and I will also be posting solutions to the midterm. Okay? All right. I love you all. Like I said, I'm going to open up a Zoom meeting now for the next 2 hours. And that 2 hours is strict because I got another Zoom meeting at 11 a.m. Okay? Absolutely bananas. I love you. I hope you all are taking care. get that post-lecture slip in.